So, I promised you at the end of the last video that we were going to talk about how we actually use dimensional analysis specifically for chemistry, and we actually use it for a slightly scary sounding thing called stoichiometry.
That sounded funny.
Yeah,
Sorry.
Stoichiometry is a funny sounding word. Blame the Greeks. All it is the calculation of relative quantities of reactants and products, which sounds really stuffy. What it's really telling us is how much we can make or how much we need to start with in a chemical reaction. Because if we're trying to make something, we don't want to just start with infinite quantities and hope that we get the amount we wanted or we needed. Especially if you're working in a big company that's making these things, you can't just make lots and hope it works out.
Yeah.
So we're going to use dimensional analysis and some of the stuff we've already learned in chemistry to figure out how much we can make or how much we need to start with. That's all these problems are going to be.
Okay.
So we can actually use stoichiometry on really simple everyday things like making a peanut butter sandwich.
That sounds good right about now.
Right, so this is our balanced equation of a peanut butter sandwich. We're going to take 2 slices of bread and a tablespoon of peanut butter and 3 teaspoons of jelly, and we're going to make 1 sandwich. So what are our reactants in this equation?
The reactants is what we're starting with. So we're starting with 2 slices of bread, 1 tablespoon of peanut butter, and the 3 teaspoons of jelly.
Okay, and what is our product?
Our product will be the sandwich.
All right.
Peanut butter sandwich.
1 peanut butter sandwich. So one of the things we can do is figure out how much product we can make from one of our reactants. So in this case, we want to know how many sandwiches we can make from 24 slices of bread.
So you said we can do dimensional analysis. I mean, could I do the railroad tracks?
We're going to do our railroad tracks. And I know a lot of you are thinking, well, but I know how many sandwiches that is. But we want to show you the process on a simple problem so that you believe us when we give you a complicated problem that the process really works.
Okay.
So we're going to do dimensional analysis even though you're thinking, but I know the answer. All right, so we're going to start with what we're what?
Okay, so we're going to start with what we're given, which was 24 slices of bread. 24 slices.
All right, and what do we want to figure out?
We want sandwiches.
All right.
Okay.
So where are we going to put what we're given?
Okay, we're going to put what we're given top left, 24 slices. There we go.
Okay. And now, if we want to compare 2 substances to each other that show up in the same chemical reaction, we can actually use the ratio that the reaction gives us. So what does the reaction tell us about our slices of bread? How many slices of bread do we need when everything works out like we want it to?
So, according to the equation, if we have 2 slices of bread, we can make 1 sandwich.
So that actually works as a unit conversion because they're compared to each other in the reaction. So if we've got slices of bread on top,
so that means I want slices here on the bottom so that we can cancel.
And our number that came with our slices in our reaction is
2.
2.
Okay.
And then we're trying to get to how many sandwiches we can make. What do we know about our sandwiches from our reaction?
And we know if we have 2 slices, we can make 1 sandwich. Okay. And that's what we want.
That's what we want.
Sandwiches.
So
okay.
we're done now. So let's figure out our math.
So 24 divided by 2 because one is above the other. So 24 divided by 2 is... Oh, look at that. It was the 12 sandwiches that I thought. Yeah,
it's the 12 sandwiches that all of you were sitting there going, but we know what it is already. Again, this is so you believe us later when we tell you that way more complicated things actually work the same way. All right, so that was a reactant to a product. We can also use it to compare reactants to reactants, and the math is not going to change. It's still going to be dimensional analysis, so we're still going to need to start with...
Still going to start with our given...
Which in this case is...
36 slices of bread.
Okay.
And we want, let's see, how many teaspoons of jelly. So teaspoons of jelly. All right, so we're going to set it up the same way. Here are the tracks. We've got 36 slices. Let's see, slices goes on the bottom so they can cancel.
And again, if we're comparing two substances, the place we've got our substances compared is our reaction.
Okay, so 2 slices of bread.
Okay, gets us how many teaspoons of jelly?
Okay, so if we're going to be using 3 teaspoons of jelly.
Right, so it doesn't matter if your two substances are on the same side of your chemical reaction. You can still use them. So wherever they are on the reaction, just look at the ratio the equation gives you.
Okay.
So that, are we where we want it to be?
Yeah, we wanted teaspoons.
Yeah.
So what we can do then is multiply 36 times 3, and then divide that number by 2.
Okay.
Right.
So that's going to get us
54 teaspoons of jelly. That's a lot of jelly.
And if we wanted to, we could actually convert that to other things, but that's a later video. For this video, we're just going to go one step based on comparing one part of our reaction to another.
Okay, so
how we apply this to real reactions, we're going to do what we just did, only instead of peanut butter and jelly and bread slices and sandwiches, we're going to have actual chemical substances. And when we're comparing our substances, we're going to do basically what we just did. We're going to compare our coefficients from the balanced equation. And that's going to get us what we call a mole ratio. So let's say we had a reaction like N2
okay, so N2
plus 3H2
3H2
gives us NH2NH3.
2NH3.
And it's a balanced reaction. How do we know it's a balanced reaction?
We have the same number of each element on both sides. So, 2 nitrogens on both sides, 6, because that's 3 times 2, and that's 2 times 3, 6 hydrogens. Okay, so we've got the same number of elements on both sides.
So it's a balanced equation following the law of conservation of mass. If you don't remember how to balance things, check with us. We can help you out. All right, so we can just do all mole ratios we could possibly have. So for every 1 mole of nitrogen we've got, we're going to put that on. So let's start with 1 mole of nitrogen on top.
Okay, so 1 mole of nitrogen.
For every 1 mole, how much hydrogen gas do we need?
Well, okay, we're using the coefficients from the balanced equation. The coefficient in front of the hydrogen gas is 3 moles of hydrogen gas. Okay.
And for every 1 mole of nitrogen gas we use, how much ammonia can we make?
1 mole of nitrogen gas, we can make 2, because that's what the coefficient is, 2 moles of nitrogen, of ammonia. All
right,
gas.
And we can actually just keep comparing all of our reactants to all of our products.
Boom.
So as you can see, you can compare any of your products to any of your reactants to anything as long as it's in your same equation. If you don't understand how we get there, flag your teacher down, get him to explain. But yeah, you can compare any part to any part. The nice thing is we typically will only need one of these comparisons. We're just showing you that you can compare everything. So let's look at how we can actually use that.
All right.
So we can just look at a really easy example of how we use that. So let's say that we know that we're starting out with 3 moles of nitrogen gas.
Okay. So that would be the given. 3 moles of nitrogen gas.
Okay. And we want to know how much hydrogen gas it's going to take us.
Okay, so we want moles of hydrogen gas.
All right. And so this first part you know. What are we going to start with?
All right. So when we draw the railroad tracks, it's 3 moles of N2.
And then...
And N2 is going to be on the moles of N2. I'm going to give myself a little bit of room. Moles of N2 are on the bottom.
All right. And we're trying to get to moles of H2. And we know from looking at that balanced equation we just wrote down
that, let's see, 1 mole went with the N2, that was the coefficient, and then H2, the coefficient was the 3.
All right, so these are, remember, our coefficients from the balanced equation. Anytime you're trying to compare two substances.
You said they are the coefficients from the equation.
Right. So that's where those numbers came from. Anytime we're trying to do this.
Okay.
If you've already got moles and you're trying to get to something else, use the coefficients.
All right.
All right. So now we're going to do our math.
All right, they're next to each other, so we can multiply. That means 3 times 3 equals 9. Let's see, those canceled out. The moles of nitrogen and the moles of nitrogen. Right? So we cancel out. Okay, so that would be the whole unit. So 3 times 3 is 9 moles of hydrogen.
See? Okay. And so we haven't really changed our math from what we were doing in dimensional analysis, what we were doing making peanut butter sandwiches. We're just doing actual chemistry now.
We're just changing the stuff that we put in. Mm-hmm. Oh, okay.
Yeah, so don't worry about these aren't units you're terribly familiar with. Just keep following your math, trusting where things go.
Okay. Very cool.
All right. So now we've got some guided practice problems for you to try. Try setting it up just like we did here. Pay attention to your coefficients. And then come back and join us when you get stuck or when you've got your answers.
All right. Sounds good.